Hello everybody, and welcome back to Chapter 1 in our Damage Control Assistant Senior Enlisted Curriculum. I'm Lieutenant Timothy Mueller, and I'll be the instructor for this lesson on moments and moment couples. Now, if you've been following my other videos, you've probably gotten pretty tired of me talking about moments and moment couples all the time. You're probably wondering, what does this have to do with ship stability? Well, we're going to start introducing in this chapter righting arms and righting moments. And then from there, we can actually look at something that's called the metacentric height, GM. And that's going to give us an initial number that's going to say if we are currently stable or unstable. But for now, let's go back into moments. Let's do a quick example problem with moments. Then we'll do an example problem with moment couples. Then we're going to end the lesson and we'll go on to the next video where we get more and more into actual ship stability. And moment couples. Just to refresh your memory, a moment is a force times a distance, and a moment couple is two forces of equal magnitude acting along parallel lines in opposite directions. Not the same line, however, they have to be parallel in opposite directions. Let's go into an example problem here. So here's the prompt for this problem right here. All right, so after that prompt, what do we have? We have a bolt whose thread diameter is 1/2 inch. And we also have a wrench that's 1 foot long. We're trying to break this bolt out of whatever's holding it down. So we have to exert a moment to break it out. We have to exert a force that's going to, in turn, make a moment onto the bolt. We found out that we broke it free when we just barely went above 50 pounds, which means that at 50 pounds, the moment that we were putting on the bolt is the same as the moment that the rust or whatever is holding the bolt in is in the opposite direction. And then once we go a little bit above 50, then we break that bolt free. We want to find out what is the force that rust or whatever it is holding those threads in. So we have two moments here, all of them acting on this axis, right in the middle. We are first going to look at our moment, what we are exerting on the bolt. So we put a force of 50 pounds, 1 foot in distance. We're going to turn this foot into inch pounds, and we're going to look at everything from inches. So 1 foot, we all know, is 12 inches. Now we go into the formula for a moment. A moment equals force times a distance. We know what the force is, it's 50 pounds. We know what the distance is, it's 1 foot, or 12 inches. Now what we do is just take 50 pounds times 12 inches, and we get 600 inch pounds, which means that at that moment, right before it broke free, when the moments are equal, we are exerting 600 inch pounds of torque, of moment, onto this bolt. Newton's third law says for every action there's an equal and opposite reaction. So we know that the reaction coming back is the same. The moment is the same. So the threads have a moment exerted on them that's 600 inch pounds. So yeah, 600 inch pounds is the moment. We know what the distance from the axis is. That's 1/4 inch. The thread diameter is 1/2 inch. But from the axis of rotation, we have to take the radius, or half of that, which is 1/4 inch. So now we just have to solve for this FR, or reactionary force. So we just take 600, we divide it by 0.25, and we get the FR equals 2,400 pounds, which means that at this moment, those threads are actually forcing more than a ton of force at that small distance. Or, if you want to look at it the other way, all you have to do is exert 50 pounds of force 1 foot out to overcome a 1 ton or over 1 ton force that's acting 1/4 inch away from that axis of rotation. All right, so that was moments. Let's take a look at moment couples now. So in this problem, we have this bar right here, and it's pinned down at this point P. We have two forces, each of 2 pounds, so they're equal, and they're acting along parallel lines in opposite directions. As you can see here, it's pointing up, here is pointing down. When we talk about moments, we have to define what's positive and what's negative. In this perspective, we're going to take anything that's counterclockwise as positive. So I put this up in the upper right corner here, so whenever you see anything that's causing a counterclockwise moment, that's going to be considered positive. Transversely, anything that is clockwise is going to be imparting what we'll call a negative moment. Now we want to consider what the moment couple is about point P, about point A, and then point B. A is 1 foot away from P, as is the other side of the bar is 1 foot. And this B, this isn't drawn to scale, but B is 5 feet out. And this is just to prove a point about moment couples. So B is all the way out somewhere around here. We're going to take a look at the moments, and we're going to use the distances from point P to calculate the moment couple. We're going to use the distances from point A to calculate that couple, and also point B. And we're going to see, if you can look at right here, all the moment couples are going to be the same, no matter where you take the reference point from. So let's start right now. We have this left moment, which we'll just call left, and then we have this right moment, which we'll call right. We know that a moment is just a force times a distance, so we're going to take the moment of each of these forces, add them together, and we'll see what the moment couple is. So about point P. So right now we're looking about point P. This left moment is imparting 2 pounds down, 1 foot away from P, and it's going counterclockwise. So we're going to consider this to be positive. So you have 2 times 1 is 2 foot-pounds. Likewise, we have another 2 pound force, 1 foot away, and it's going counterclockwise. So that's also positive. So we have a 2 foot-pound moment, a 2 foot-pound moment, both acting in the same direction, counterclockwise. So we add them together to get 4 foot-pounds. Next up, let's take a look at point alpha, point A. Nothing's going to change with the forces themselves. However, what is going to change is the distance from that point. So even though they're acting on point P, or about point P, we're going to take a look at this alpha here. So we have a 2 pound force acting straight down into alpha. There's no perpendicular distance from alpha to this force, so the distance here is 0. So we have a 2 pound force acting 0 feet away, which means that it's imparting a 0 foot-pound moment onto it, which means it's just no moment at all. However, all the way over here at this right side arrow, we have 2 pounds. However, it is acting 2 feet away. So we have 2 pounds times 2 feet, 1 plus 1 is 2, equals 4 foot-pounds. Now we have 0 plus 4, since we just call this neutral, 0, and this is counterclockwise, so it's positive, equals 4 foot-pounds in the positive direction, which is exactly the same as when we took all the distances to be about point P. Now let's take a look at point Bravo. Remember, Bravo is 5 feet all the way out here. We're going to take those distances around B and see if we get the same exact thing as we got for P and A. So on the left side, for this arrow, we have 2 pounds pointing down, but we're 5 feet away. So from point B to where 2 is acting on, is 5 feet. However, if we look at it, if we're rotating about point B, this arrow is actually imparting a clockwise moment onto this. So it's going to be negative. So we have negative 2 times 5, and you can put the negative either way, it's more of a notation thing, equals negative 10 foot-pounds. Yeah. Now we look at the other force, the other moment. We have 2 pounds, nothing's changing with the actual magnitude of the force, only thing changing is the distance. We have from B to get all the way there, we have to go 5 plus 1 plus 1, which gives us 7. So we have 2 pounds acting 7 feet away. So we're going to multiply 2 by 7, we're going to get 14. Now if we look at it, about point B, this arrow makes everything want to go counterclockwise. So that's a positive moment. So we have a positive 14, a negative 10, we just add them together and we get a positive 4 foot-pounds, which means that no matter where we take this reference point, it can be B, A, it can be all the way over here, or we can even put a point down here or up there. the moment couple is going to be the same. The summation of all the moments is going to be the same. So we can say, no matter where we are, this bar will always be experiencing 4 foot-pounds of total torque or total moment in the counterclockwise direction. Now you're probably thinking, in the last example, or the very first example, I talked about a bolt and the wrench. Now I'm just talking about a bar that's pinned down. How does this have any relevance to ship stability? Now remember, I talked about displacement, buoyancy, and the center of gravity. How the center of gravity is the point through which gravity acts, and the magnitude of that force is just the weight of the object, the weight of the ship, which is the mass times the gravitational constant. Archimedes' principle states that the water, the buoyancy force, is equal and opposite to the force of gravity. So we have a center of buoyancy through which that force of buoyancy acts through, that is equal and opposite to the force of gravity. So we'll be having a force of gravity down and a force of buoyancy up. If these are directly along parallel lines with no distance in between them, then there's no net force, which means that nothing's going to move. However, if we move the boat to a side, which, as we saw in chapter 0, is going to move the center of buoyancy, that center of buoyancy will move over, and that will actually cause a moment couple. We'll have 2 equal forces, because nothing has changed with the weight of the ship. 2 equal forces along parallel lines, because buoyancy is always acting directly up and gravity is always directly down. They're along parallel lines, equal magnitude, and there's a distance between them. So you saw here, we could either find some point in the middle, or we can just say, okay, right where gravity is, where that line of gravity is, we can take a point there, and then we can use the distance from the line of gravity over to where buoyancy is acting. This distance, if we call this gravity and this buoyancy, this distance is what we're going to be calling the righting arm. Okay? The distance, the perpendicular distance from gravity over to buoyancy. Okay? And as you can probably intuitively think, if you multiply that righting arm by the force of the displacement, you get the righting moment. So that does it for lesson 2 of chapter 1 on moments and moment couples. The next lesson, we're going to actually take a look at a diagram of a ship that's rolled over to one side, and we're going to see how the center of buoyancy and center of gravity are acting with each other. You saw this diagram before in chapter 0, but I'm going to refresh your memory now before we actually get into what's called the stability triangle. When we get into the stability triangle, then we're going to see righting arm, righting moment, and we're going to start seeing the metacentric height, which I mentioned before is very important when you're trying to find the initial stability of a ship or anything that's immersed in water. But for now, I'm Lieutenant Timothy Mueller. I hope you enjoyed this lesson. I hope you have a great day.